In this section, 5.6, we're looking at inequalities in two triangles and indirect proof. So we're going to start off with inequalities in two triangles, and we're going to call that the hinge theorem, and that's theorem 5.13 or 5.13 in our notes. It's a little wordy in what we have, but let's get through it and we'll see that it's actually really just a form of side angle side. So if two sides of one triangle are congruent to two sides of another triangle. If I look, I have Vx, Rt, both have a single marking, VW, RS, both have the double markings. So they match up. Then I have here, and the included angle of the first is larger than the included angle of the second. 88 is bigger than 35. Okay, so side angle side, 35 there, side angle side, 88 there. Okay, so then we get the third side of the first is longer than the third side of the second. So because this angle's bigger, Wx is bigger than St. So Wx is greater than St, and that's by what we call our hinge theorem. Now, if we think about this one, think if we almost have a door opening. So I have a door that's opening, and the door swings on that arc on it. But when I have the door open, there's a distance I can measure. Then I open the door a little bit more, and there's another distance I can measure. The angles have changed, but the side that the door is on, that side from the corner of the door back to the frame, is now bigger. So it's now allowing us to compare, and really that's what we're doing. The sides are the same, but it's as it's opening up. We could take our pens and think of it. I have my sides, they open. That makes a triangle. I increase the angle. Now the tips of the pens are even further away. I put them closer together. The angle gets smaller, and the tips of the pens are closer. That's really what we're looking at the hinge theorem. Now, the converse of the hinge theorem, if two sides of one triangle are congruent to two sides of another triangle, again, AC, CB, DF, FE, there's our congruence, then the third side of the first is longer than the third side of the second. Okay, 12 and 9. So this is now bigger than 9. Well, it's kind of going the opposite direction before. So since this is bigger, 12, than 9, I know that C should be bigger than F, which says then the included angle of the first is larger than the included angle of the second. So again, opposite, and C is now bigger than F because it's open more. Now, if we take our pens and we open it up, this is now further apart than if I tighten it up, so the angles are bigger. Since the angles are bigger, that's looking at the converse of the hinge theorem. So let's look at the examples, and that's going to help us see them a little bit better. So really it's just comparing the two triangles. The key thing we look for is its side angle side like. So two sets of sides match, and it's the angles in between. So I have sides here. BD is reflexive, so there's my other side. So it's really like a mirror image here. Now, 36 degrees is this angle, 32 degrees is that one. We'd easily see that 36 is bigger than 32. Well, since that's bigger, that means that AD is bigger than CD. That one's opens 36, this one only opens 32. AD is going to be open more, so we put in our greater than inequality. Come over here. I have QT, SU. There's my sides. SRQ, or SRRQ is our side. So we can even draw them side by side. So I know Q is at 22 degrees. I know S is 24 degrees. So looking at it, which one's going to be bigger, TR or UR? Well, 24 degrees means UR is going to be bigger. So our inequality going that way. Third one, I have reflexive. So I have angle 2. And it has a side that's 39. And I can flip this one around and I get angle 1. That has a 42. Well, 42 is bigger than 39. That means angle 1 has to be bigger than angle 2. It's open more. Okay, now let's take this idea and look at a couple triangles together. So I want to find the shortest segment in the diagram. I have two triangles. I have ABD in this one and BDC. First off, we have to find the third angles in each. We know the sum of all the angles in a triangle, where the interior angles is 180. So that means angle A is 38, and B in the right triangle is 36. Again, I'm adding up the two I know, subtracting from 180. Now I want to find the shortest segment in the diagram. Well, if we go back a step, and we can find really the shortest segment in each triangle. So if I look at the left triangle, the shortest segment in this triangle is opposite the smallest angle. 32 is the smallest angle, so that means AB is the shortest segment in triangle ABD. In the right triangle, 30 degrees is the smallest angle, so that's opposite BD. So BD is the smallest segment in that triangle. Now, I have to find a way to put them together. If I notice A, B, D, they both have, we think of them as our candidates. Our candidates for the shortest segment. It could be AB, it could be BD, but the key thing is ABD has them both. So ABD tells us it's either this angle, or this side, or this side. So we use that process to narrow it down. It's one of these two sides. Now within just this triangle, AB is opposite the 32, while BD is opposite the 38, meaning AB is our shortest side. Let's try that again with a little nicer numbers. I have 80, 60, 90, 50. Need to finish out each triangle. 80 and 60 is 140. That leaves 40 left over at angle A. 90 and 50 is 40. Leaves 40 left over in angle B, or I should say CBD, in my right triangle. Or triangle on the right. Oh, they're both right. It's a right triangle as well. But I need to find the shortest segment. Now, looking at all of this, just because it has the smallest angle doesn't always necessarily mean that. If I jump back to this last one, 30 degrees was my smallest angle in the whole thing. Well, we found out it wasn't necessarily the shortest side. It just happened to be the shortest side in that triangle. So back over here. Looking at just the left triangle, I have 40, 80, 60. Opposite the 40 is BC. So BC is one of my candidates for shortest side. That's my nominee from the left triangle. On the triangle on the right, or right triangle, I have 40, 90, 50. Well, 40 is the smallest. Opposite that is CD. So our nominee from the triangle on the right is CD. If I draw them together in the same triangle, that's the key. Then I can see, well, I have 40, 50, 90, C, B, D, and these are my two candidates. Well, 40 is the lowest, smallest angle, so that means CD is our shortest side. So it's working through, narrowing it down to 2. Once you get to 2, looking at the triangle they're both in, and finding which one's the shortest. If they were not in the same triangle, then, well, maybe it's not enough information, or maybe we just made a mistake along the way, but go back and make sure it works. So now let's change gears and look at indirect proof. Indirect proof, we have a few steps. And now, first of all, it's a proof where you start by assuming temporarily that the conclusion is false. Again, a conclusion is when we have that if-then statement. The conclusion is what follows the then. So we're going to assume that's false first. The next step is to show that this temporarily false conclusion leads to a contradiction. So something, oh, it doesn't work, here's why. So we have to find some way it fails. And by showing that contradiction, what we started with assuming in the beginning can't actually be false. So that's the quick version to what we're doing. If we look at the steps we have three rules which you should already have down. Identify the statement you want to prove, then assume temporarily that this statement is false by assuming the opposite is true. Reason logically until you reach a contradiction. Point out the desired conclusion must be true because the contradiction proves the temporary assumption false. So, that's a mouthful there. Let's look now. Write an indirect proof for the given statement. So we say if x plus y doesn't equal 14 and y equals 5, then x doesn't equal 9. So this is what we're going to assume the opposite true. So opposite of x not equal to 9 means x equals 9. If I assume that, then I know that x equals 9 and y equals 5 gives the equation 9 plus 5 doesn't equal 14. And that's just substituting into what we have. Well, 14 doesn't equal 14 is a contradiction. $14 does equal itself. This shows that, well, we can't assume x doesn't equal 9 because that leads to the contradiction. Therefore, x can't equal 9 in order for this to work. If we assume it does work, well, if we assume x equals 9, then we do get the contradiction. We can't have it. Therefore, it can't be true. So it's not necessarily doing a proof as we've done before. We assume the conclusion is true and then find how it doesn't work. So let's work through more of them. Let's jump to these practice problems here, and we're just going to first make sure we get the assumption correct that we start with, and then see how it works through when we find it. So, given x is an odd number, prove x is not divisible by 4. Normally we'd have to take this, work through our steps, and arrive to the end showing what we want to prove. We're going to do it differently here. We're going to assume the opposite of our conclusion. So x is not divisible by 4. We're going to assume x is divisible by 4. That's first step. Well, if we assume x is divisible by 4, then that means, well, first of all, x is even. Well, if x is even, it can't be odd. Therefore, x is not divisible by 4. Now, we would write out those steps that we said in between. If it's divisible by 4, then it's also even, and it can't be both odd and even, so that would be our contradiction. But key is we're getting our first step, and we're seeing how we get to that conclusion. Next one, given a and b are odd integers, prove that a plus b is an even number. First step, assume a plus b is an odd number. Now if I add an odd plus an odd, because a and b are both odd numbers, I get an even. Just think of two odd numbers, adding them together. They come out to be even. They always will. Well, this is not an odd number like I just assumed. Therefore, a plus b is an even number. It's almost saying the opposite cannot work, therefore it must be true. Last one, if x and y are odd integers, then xy is odd, or the product of x and y is odd. So we're going to assume x times y is even. That means if I have x and y are odd, that an odd times an odd equals even. Well, if I think of two odd numbers, say 5 and 7, multiply those together, I get 35. Well, that's odd. If I take 3 and 5, 3 times 5 is 15. Well, that's odd. Well, actually, these need to be odd numbers because our rules of multiplication tell us an odd times an odd equals an odd. So, since it can't be even,